Hi there. Hello, guys. So, what's up? What are we doing here? I'm tired already. Uh, okay. I'm gonna do a little bit of this here because it's getting hot. Okay, good. Determine the components of the force F. This is the force F that act along the rod AC. Okay, now this is where you push the brakes. Stop there. Every time a problem asks you what is the value of the force that acts along a line? How much of this force acts along this axis? What are the components of this force in this direction? The problem is screaming at you, dot product. That's it, plain and simple. Dot product. Of what? Dot product of the force and the unit vector of the axis. That's what you have to do. And that will give you at least the first part of the problem. How do you get the force in Cartesian? That's a different story. You know, there are different ways, right? Alpha, beta, gamma, projection angles. You can calculate position vectors in order to get the unit vector. There are several ways. Uh, and how do you get the second part? That's also another point. This perpendicular, because this is going to give you along the rod, not perpendicular to the rod. So let's start from the beginning. First, find the force. That's the first thing. How can we find the force in this particular problem? Well, we have the magnitude of the force, and we have coordinates here, you see, or the possibility of getting coordinates. Because if I can get the coordinates, I can get this and multiply that by the unit vector BD. And the unit vector BD is just the position vector BD divided by the magnitude of the position vector BD. So the first step will be done. The second step will be find the unit vector in the direction of the rod, and just the third step is just dot multiply them. And of course the result is going to be a scalar because it's dot product. Okie dokie. So I know that I'm going to need the unit vector BD, and I'm going to need the position vector BD, and I'm going to need the unit vector AC. So bottom line is we will need coordinates of all of these points. So what are the coordinates of the point A? 0, 0, 4, because it's exactly over the z-axis. What are the coordinates of the point 6? That would be 4 in x, 6 in y, 4, 6, 0, because it's over the xy plane. What are the coordinates of the point C? 3 in x, but it's not 3, okay? It's negative 3. Why is negative 3? Because this is the 0, this is the positive side, so that's negative. Negative 3, 4, 0, because it's over the xy plane. And what are the coordinates of the point B? Oh, danger, Will Robinson, danger. It says it here, it's located at the midpoint of the rod. So if you are trying to locate a point that is at midpoint of something, all the coordinates are going to be midpoints as well. So instead of negative 3, that would be negative 1.5. Instead of being 4, it will be 2. And instead of being 4, it will be 2. Easy peasy, lemon squeezy. You know where is that coming from? Easy peasy, lemon squeezy. Okay, Google it. That was a commercial, really old commercial of dish detergent. But you can Google it. I know some of you will. Okay, let's start expressing the force in Cartesian. I need the position vector BD. How do you get position vector BD? Coordinates of B minus D minus coordinates of B. 4 minus 1.5. That means 5.5i. 6 minus 2, 4. J. 0 minus 2 minus 2k. Divided by the square root of 5.5 squared plus 4 squared minus 2 or plus 2 squared. That will be the position vector BD divided by the magnitude of BD, which will give you the unit vector in the direction of BD. But the unit vector in the direction of BD is the same unit vector of the force, meaning if I multiply this by the magnitude of the force, then I will have the force in Cartesian. Force in Cartesian will be will be soon will be let me do the denominator first. Square plus 4 square plus 2 square 5.5 square plus 2 square plus 2 square 0.5 square root 7.0887. Okay, I'm gonna do 600 times 5.5 divided by that. That would be 465.28 I. Now this is 4, but the rest is the same. So I divide by 5.5 and multiply by 4. You do it whatever way you want, okay? This is just for saving time of doing this. Plus 338.57J. And I know that now this is going to be 2, so it's going to be half of this one. I divide this by 2, 169.28 K. And the force are in Newton. That's the force. Next step. What is the next step? The next step will be finding the position vector or the unit vector in the direction of the rod. How do I find the unit vector in the direction of the rod? Coordinates of C. The unit vector will be AC, right? So coordinates of C minus coordinates of A. So basically what you have to do is the unit vector in the direction of the rod. Now I'm gonna try to put all of these in one all thing. Oh no, let's do it by parts. So if I get AC, that will be what? Coordinates of C minus coordinates of A. Negative 3 minus 0, negative 3i. 4 minus 0, 4. Yeah. 0 minus 4, minus 4k. Now if I divide that by the magnitude of AC, magnitude of the square root of 3 squared plus 4 squared plus 4 squared, that is giving me what? The unit vector AC. What is the unit vector AC? That will be, this is 9 plus 32 of 41, square root of 41. So 3 divided by the square root of 41 is negative 0.4685 in I plus, I'm just going to divide by 3 and multiply by 4, which is the same thing, 0.6247J minus 0.6247J. That's the unit vector in that direction. And now we just dot multiply these two. How do you dot multiply? It would be this times this plus this times this plus this times that. So let's try to do that. Well, this is negative, so I'm going to start with negative 465.28 times 0.4685 plus 338.57 times 0.6247 minus times minus is plus 169.28 69 times 28 times 0.6247, and that gives you 99.27, or 99.3. So 99.3 Newton. Remember, it has to be a scalar. So the this is the force acting along AC. But the problem is asking also the how much of the force act perpendicular to the bar, perpendicular to AC. Well, there are two ways of doing this. I could find, because if I know the equation of the line AC, I can find the equation of the line perpendicular to that. Or I can be just smarter and remembering what I know, that if I have, for example, Fx and Fy, one direction perpendicular to the other direction. So if I have that, I can say that F squared is equal to Fx squared plus Fy squared. Or I can say that F squared will be the force acting parallel, or the component of the force parallel acting to AC squared, plus the component of the force acting perpendicular to AC squared. And I know this is 600, and I know this is 99.3. So I could find the component of the force perpendicular to AC squared, and that will be 600 squared minus this, when I pass it to the other side, minus 99.3 squared, which implies that perpendicular force is going to be the square root of this, and that would be 600 squared minus the value that we got before square, and the square root of this, 591.73. So that would be the force, or the how much of the force acts parallel to AC, and how much of the force acts perpendicular to AC. Just applying this little trick, it shortened the problem like a lot, because then you have to remember what is the equation of the line, what is the perpendicular equation of the line. Oh, the slope has to be the inverse, or negative inverse of whatever, and then the point is this, and create the equation, and it's a pain. But try to work smart, not that hard, but smart. See you in the next video, guys. Have a good day.